Dear students, very good morning. Today we are going to discuss the topic laser. Laser is an acronym, stands for light amplification by stimulated emission of radiation. So what is the meaning of this one? The light means is one form of energy. Amplification means to raise the strength of the signal. Light amplification means to raise the strength of the light beam. By what process? Stimulated emission of radiation. Stimulation means activation. So, laser is instrument in which the strength of the light beam is increased by activated emission of radiation. What is the stimulated emission of radiation? We are going to discuss in the basic concepts. Before that, we will have a look on history of laser. Laser is invented in 1958 by Charles Towns. He is a Nobel Prize winner and also Arthur Swallow of Bell. These laboratories are based on the particle wave duality given by the idea given by the Einstein. And coming to this laser source, the important is if you take any light source, the light will travel in all the directions. So divergence is all the directions. And if you take a flashlight also, divergence is somehow less when compared with the sun or any ordinary light. But divergence is there. But coming to the laser, divergence is not there. It is almost straight line path. I can't tell divergence is zero, but the divergence is very, very less. Because of its less divergence, and if you see the power density is very, very high. If you compare with the sun, the power density is 5 into 10 square. If you take carbon dioxide laser, it is 5 into 10 power 6 watt per centimeter square. That means 10 power 4 times higher. 10 power 4 means 10,000 times higher than the sun power density. Power may be less, but power density is very, very high. This is very useful for number of applications in the industry. And coming to its characteristics, which makes the laser to useful for a lot of applications in all the field, is one is highly directional. That means propagating almost right hand path. Means divergence is very, very less. Highly monochromatic. They are having only one frequency or one wavelength. And highly coherent. That means they maintain constant phase difference. And finally, high intensity. Intensity is very, very high. If we discuss these characteristics elaborately, the first one is directionality. If you take any ordinary light, light will propagate in all the directions. If you take laser, so the divergence, if you see, this is very, very less. This divergence angle is we can measure as 1.22 lambda by 2 W naught. This lambda is the wavelength of the light coming out from the laser, and W naught is the radius of the beam. So also we can measure in another way. If the diameter of the beam is A1 and A2 at a distance of the D1 and D2, then we can measure the divergence angle is equal to A2 minus A1 by 2 into D2 minus D1. And coming to the other characteristics, monochromicity. So monochromaticity, what is this one is the beam is having only one kind of wavelength. That means one kind of frequency. But it is not exactly one kind of frequency. There is some wavelength dispersion is there, delta lambda, but that is very, very less. So laser is we can consider almost monochromatic, but exactly monochromatic. And coming to the other one, coherence. So I think you know about the coherent sources. If we take two waves, if they maintain constant phase difference, then we can say the two waves are coherent waves, or the source which are providing those waves are called coherent waves. The coherence is two kind here: temporal coherence and spatial coherence. With respect to time, that is called temporal coherence. With respect to space, that is called spatial coherence. For example, if we take a wave, if it is a continuous wave, then definitely is with respect to time, it is coherent, no doubt. That means one position, if we take this position is crest, that is always crest. This one position is trough, it is always trough. So with respect to time, always one position is crest, that position is always crest with respect to time. Then we can say it is temporally coherent, but that will not happen. That means we can't get continuous wave. There is some break will be there. Even though there is some break will be there, even though the presence of small break between these discontinuous waves, but the time is very less. So when compared with this length of the wave, we can say almost they are temporally coherent. With respect to this coherent length, the gap between these two is very less. Then we can say there is almost temporally coherent because of correlation they can maintain. But generally, if it is discontinuous wave, so there is a chance of lack of coherence because of the time lapse between the two discontinuous waves may be high. But if it is very less with respect to the coherent length, then we can say they are temporally coherent. And next one is spatial coherence. If any 2 points on the cross section of a wave like this, if you take the different if you see, so these waves are not in coherent. They have not maintained constant phase reference here. But if you take this one, see, all cluster beams like this, they have maintained constant phase reference. So with respect to space, with respect to different points on the wavefront, they maintain constant phase reference. We can say those are spatially coherent. So laser beam is both temporally coherent as well as spatially coherent. And coming to the brightness, we already discussed this power density is very high. Because of this one, the laser beam is having high intensity. So if you take is brighter than the sun. Now the concept related to laser absorption, spontaneous emission, and stimulated emission. What is absorption is? If we take any system, the system is made up of atoms. These atoms did not possess all the energy values. They can take some discrete energy values only. E1, E2, E3, E4, E5 like this. But most of the atoms are in the lowest energy level because the lowest energy state is a more stable state. Because of high stability of the lower energy state, most of the atoms are present here. If you give some energy, that energy is equal to the difference of two energy levels, then the atoms in the lower energy level absorbs the energy and goes to the exit state. This phenomena is called absorption. This phenomenon is called absorption. So for our convenience, I am working with two energy levels only, E1 and E2. E1 is the ground state and E2 is the first exit state. And most of the atoms are in the lower energy level because the lower energy state is the high stable state. Now I am giving some energy in form of radiation. The atom in the lower energy level absorbs the energy and goes to the exit state. This phenomenon is called absorption. The number of atoms which are going to the exit state depends on what factors, how many atoms available in the lower energy level. Because more atoms are available here, more will be excited. That's why how many atoms available in the lower energy level. If more are there, more will be excited. That means the number of atoms which are going to the exit state by the phenomenon of absorption is directly proportional to N1. At the same time, how much energy we are supplying, that means how many photons we are supplying. That means That also depends on the energy density of the incident radiation. The energy density of the incident radiation we are showing with the U of nu. What is the U of nu? Energy is a function which gives the energy density of the incident radiation. Here nu is the frequency of the radiation. So the number of atoms which are going to the excited state by the phenomena of absorption is directly proportional to the number of atoms available in the low energy level N1 and the number of atoms which are going to the excited state depends on another factor, that is the energy density of the incident radiation U of nu. So the number of atoms that are going to the excited state is directly proportional to N1 into U of nu. That proportionality is replaced by a constant B12 known as Einstein's absorption coefficient. So the number of atoms that are going to the excited state by the phenomenon of absorption is directly proportional to B12 into N1 into U of nu. Next concept is spontaneous emission. If the atoms are going to the excited state, they can't spend in the excited state for long time. Why? Excited state is a unstable state. They are spending in the excited state for very short period, that is around 10 power minus 8 seconds. That is around 10 power minus 8 seconds. After end of this lifetime, they are coming back themselves and they lost the energy. How much energy they will lose? E2 minus E1. If that energy emitted in form of radiation, this kind of emission is called spontaneous emission of radiation, because the atoms in the excited state coming back spontaneously. What is the meaning of that? There is no involvement of any external source. So no one is involved externally here. They are coming back themselves. That's why this kind of emission is called spontaneous emission. If that emission gives the radiation, then we can say it is spontaneous emission of radiation. So the atoms in the excited state coming back spontaneously and emit the radiation, then that kind of emission is called spontaneous emission of radiation. In this, the number of atoms which are in the excited state gives the probability of coming back spontaneously. If the more are in the excited state, more will come back. Less are in the excited state, less will come back. So the number of atoms coming back spontaneously is directly proportional to N2. So that proportionality replaced by constant A21, that is known as Einstein's spontaneous emission coefficient. In that there is no external involvement. That's why it is equal to A21 into N2. And coming to the another concept is stimulated emission of radiation. It's a very interesting one. It is proposed by Einstein. Spontaneous emission of radiation is proposed by Bohr. The stimulated emission of radiation is proposed by Einstein. In this, the atom in the excited state coming back stimulatively. What is the meaning of stimulative? Activation. So with the activation, the atom in the excited state coming back. So here, if you take a system, there are N2 atoms in the excited state. Definitely they will come back after end of their lifetime. Within the end of lifetime, one photon is come here and motivate the atom in the excited state. Motivate means stimulates, means activates the atom in the excited state and come back to the ground state. Then we are getting the two photons. One is instant photon and the other one is due to transition of atom from the excited state to ground state. In this case, the instant photon did not give any energy, did not take energy. Just it stimulate atom in the excited state and follow its path. And because of that stimulation, the atom in the excited state coming back, that also gives one more photon. Both are in the same phase, so strength is doubled. So this kind of phenomena is called stimulated emission of radiation. So the atom in the excited state coming back stimulatively and emit the radiation, then that kind of emission process is called stimulated emission of radiation. So in this, the number of atoms coming back stimulatively depends on number of atoms available in the excited state and how many photons are coming for stimulation also different. So how many photons are coming for stimulation is given by energy density of the incident radiation, U of nu. So the number of atoms which are coming back stimulatively is directly proportional to number of atoms available in the adjusted N2 and energy density of the incident radiation U of nu. So the proportional replaced by constant B21, that is called Einstein stimulated emission coefficient. So the number of atoms which are coming back stimulatively is equal to B21 into N2 into U of nu. So in the absorption process, the atoms are moving from the lower energy state to higher energy state. But in the spontaneous process, the atoms are moving from the higher energy level to lower energy level. In stimulation process also, the atoms are moving from the higher energy level to lower energy level. Spontaneous is proposed by Bohr, stimulated is proposed by Einstein. So when we are discussing about any system, that can be discussed only when the system is in equilibrium. And the system is in equilibrium, the number of atoms which are going to the excited state by the phenomena of absorption is equal to number of atoms which are coming back spontaneously and stimulatively. That's why when the system is in equilibrium, the number of atoms that are going to the excited state by the phenomena of absorption, this value, is equal to number of atoms which are coming back spontaneously plus number of atoms which are coming back stimulatively. So take this equation in the equilibrium, then take this U of nu term to left hand side, then take U of nu common. If you take U of nu common here, that become B12 into N1 minus B21 N2 into U of nu is equal to A21 into N2. Then take this term right hand side, then U of nu equal to A21 into N2 by B12 into N1 minus B21 into N2. Now we take B21 N2 common. If you take B21 N2 common, then this equation becomes A21 by N2, this value is as it is, and B21 by N2 we have taken common in the denominator. Then what remains here? Here B21 into N2 is not there, so you have to divide. So B12 into N1 by B21 into N2 minus this value we have taken common, so minus 1. And according to Maxwell-Boltzmann distribution law, the number of atoms which are having energy E is directly proportional to E power minus E by kT. K is the Boltzmann constant, T is the absolute temperature. Here, N1 is the number of atoms with energy E1. So N1 is proportional to E power minus E1 by kT. N2 is the number of atoms with energy E2. Therefore, N2 is proportional to E power minus E2 by kT. Then if you take N1 by N2, that equal to proportionality we can replace equal here because both are having same proportionality constant, that will be cancelled out. Therefore, N1 by N2 equal to E power minus E1 by kT divided by E power minus E2 by kT. So E power minus E2 by kT in the denominator, that we are taking the numerator, that the equation becomes E power E2 minus E1 by kT. We know the E2 minus E1 equal to H nu. Therefore, that equation becomes E power H nu by kT. Therefore, we are replacing this N1 by N2 here with E power H nu by kT. This is the equation we obtained for energy density of the incident radiation. But already we have a radiation formula given by Planck. That formula is 8 pi H nu cube by C cube by E power H nu by kT minus 1 for energy density of the radiation. So according to Planck's radiation formula, U of mu equal to 8 pi H nu cube by C cube divided by E power H nu by kT minus 1. Now we are comparing these two equations. This equation is named as B here. I didn't put B here. It's B. And compare these two equations. Then A21 by B21 in place of this one. What we are having? 8 pi H nu cube by C cube. So A21 by B21 equal to 8 pi H nu cube by C cube, and B12 by B21 here. B12 by B21. So what we are having here? Nothing. That means 1 is there. So B12 by B21 equal to how much? 1. So therefore, B12 equal to B21. Okay. So in this way, we are obtaining relation between these Einstein coefficients. If you observe this A21, that one gives the spontaneous probability. B21 gives the stimulation probability. So spontaneous probability by stimulation probability is equal to 8 pi h nu cube by c cube. Here 8 constant, pi constant, h constant, c velocity of light constant. So A21 by B21 is directly proportional to cube of the frequency. So the ratio of probability of spontaneous emission to stimulated emission is directly proportional to cube of the frequency of the radiation. Here h is the Planck's constant. That value is 6.625 into 10 power minus 34 joule second. C is the velocity of light, 3 into 10 power 8 meters per second. Now we are going to discuss lasing action. Here we already discussed here, laser is nothing but light amplification by stimulated emission of radiation. For suppose if you are giving one photon here that stimulates the one atom, then we are getting the two photons. If you repeat the stimulation emission process number of times, for suppose I am reflecting it back by using a mirror, then these two stimulate another two, then you will get a 4. Again I repeat this one by reflecting it back by using a mirror, then the 4 will reflect back and stimulate another 4, then you will get 8. In this way, by repeating the stimulated emission process number of time, we can build a highly directional, highly coherent, highly monochromatic and high intensity beam. So that process is called lasing action. So lasing action, how we define? To induce resonance in the light beam by repeating stimulated emission of radiation. Okay. So what is the lasing action? We have to induce resonance in the light beam by repeating stimulated emission of radiation. If you want to repeat this process number of times, what we need? We must need more number of atoms in the excited state than the Lorentz state. We need more number of atoms in the excited state than the Lorentz state. That can be done only when in the system there is a presence of energy states with a high lifetime. So if you want to initiate a lasing action, there must be a necessary condition satisfied, that is presence of more number of atoms in the excited state than the Lorentz state. That is called population inversion. So what is the necessary condition for lasing action? Population inversion. What is the meaning of this one? More number of atoms in the excited state than the Lorentz state. So here if you take any system, most of the atoms are in the low range level because low range state is more stable, but very less number of atoms in the high range level. But if you want to achieve the population inversion, we have to get more number of atoms. For suppose if you take 1 and 2 here, 2 is having more concentration of atoms when compared with 1. Then we can say there is a population inversion exists between these 2 and 1. This kind of situation is required to initiate the lasing action. That's why population inversion is the necessary condition for lasing action that can be achieved only in those systems in which there is a presence of energy states with high lifetime, because high lifetime is not there. If atoms are moving to higher energy level, immediately they are coming back, then we don't have the more number of atoms in the excited state because of less lifetime. So if you want to get the more number of atoms in the excited state, there must be presence of higher energy level with high lifetime. Those energy states are called metastable states. So the necessary condition for lasing action is population inversion that can be achieved in the medium in which there is a presence of metastable states. Those media are called active medium. So the one of the component required to construct a laser is active medium. What is the active medium? The medium which is having metastable state. If the metastable states are available in the medium, but atoms are not readily available in the exit state, to excite these atoms to metastable state, we need a source which supply the energy and excite the atoms from the lower range level to high range level. That source is called source of excitation. So another component required to construct a laser is source of excitation. Its role is excitation mechanism. So after exciting the atoms to the exit state, if the metastates are available, then atoms are reaching the metastable state, then we can achieve the population inversion. Then any one atom, its lifetime is over, that will come spontaneously and emits the photon. That photon we have to reflect back to stimulate the another atom. And if you want to continue this process, we have to reflect this emitted photons number of times. For that we have to arrange an arrangement of two mirrors on either side of the active medium. One is fully reflection coating, other one is partially reflection coating. That arrangement is called resonance cavity. That arrangement is called resonance cavity. What is the resonance cavity? An arrangement of two mirrors. One is fully reflection coating, other one is partially reflection coating. So what are the components required to construct a laser? Active medium, which is having metastable state. And second one is source of excitation, would excite the atom from the lower range level to high range level. And resonance cavity, an arrangement of two mirrors on either side of the active medium. One is fully reflection coating, other one is partially reflection coating. That cavity also known as optical cavity also. Now the role of source of excitation is to excite the atoms from the lower range level to high range level. The excitation of atoms from the lower range level to high range level is called pumping. The pumping process can be done by different schemes. Those we named as pumping schemes. One is optical pumping. In that we are using an optical source to excite the atoms from the lower range level to high range level. So if you give some light energy, the atoms in the lower range level absorbs the energy and goes to the exit state. This kind of pumping is called optical pumping. For example, in ruby laser, we are using xenon flash lamp to excite the atom from the lower range level to high range level. And second kind of pumping scheme is electronic discharge. In this electronic discharge, if you take an active medium, the atoms are lower range level, and we are creating electronic discharge by applying voltage across the electrodes. Then electrons are moving from the one electrode to other electrode. They will excite the atoms and make them to go to the exit state. This kind of pumping scheme is known as electronic discharge pumping. In this process, this kind of process mostly we are applying for gas lasers. And third kind of pumping scheme is atom to atom inelastic collision. In this, the atom in the exit state, they are coming back non-radiatively and entered with the atoms in the lower level and make them to excite. This kind of excitation is known as atom to atom inelastic collision. And in the helium neon laser and carbon dioxide laser also, we are using this kind of excitation. Next kind of pumping scheme is chemical reaction. In this chemical reaction, we are creating one chemical reaction in the active medium that generates a lot of heat energy that is used to excite the atoms. In the direct conversion, we can convert the electrical energy into optical energy. That we will discuss in the semiconductor laser. Now we are going to discuss the carbon dioxide laser construction and working.